So that generates a tangential acceleration like this initially. So from that you can understand that it is a non-uniform circular motion. So by the time it's some time t, your v has become less than v naught. Like this, okay. So yes, exactly. Mg is into the plane of the into the plane of the paper, and there's another normal reaction coming out of the plane of the paper, and those two are balancing each other. Okay, so basically, if you see this diagram in a horizontal plane, this is the ring on which it's lying. So these two forces are balancing each other. See, there is this normal reaction, okay, and this surface is smooth. It's only the inner surface of the ring which has a coefficient of friction, okay, that is given to us. Frictionless stable. Right, so this is clear, Aman?
Yes, sir.
Okay, so very good. So now you can see, so at this point of time, the friction mu n is equal to mu mv square by r. Okay. So now we'll write the dynamical equation. Dynamical equation क्या हो जाएगा कि ये तो हो गया अपना centripetal. This is our centripetal force. But what about tangential force? Kinetic friction is, in this case, it will become m into minus dv by dt. This is our tangential equation. Okay. So this equation only will give us v as a function of time. That's what we want to find out now. Find the speed and position as a function. So we'll start with v. So kinetic friction is mu mv square by r. That will be equal to minus m dv by dt. So dv by dt is equal to minus mu v square by r. So dv by v square is equal to minus mu by r dt. So if we integrate this, now this is going from speed v naught to some unknown speed v as a function of time from 0 to t. Okay. So integration of 1 by v square is equal to minus 1 by v. Okay. So this should be your speed as a function of time. Okay, Aman, this is clear so far?
yes, sir.
Okay, now once you found the speed as a function of time, you can calculate the distance s, and that distance is equal to angular displacement into radius because it's arc length. Okay. So that distance will be integration of v dt. So distance traveled, the circular arc length traveled, that will become v naught r plus mu v naught t dt integrated from t equal to 0 to t equal to t. Okay, so this is an integration of this type, some constant upon, okay, this type of thing. So first of all, a comes outside, and you have this, which becomes natural log of b plus cx divided by c. So that kind of thing here. So this becomes s becomes v naught r, okay, to natural log of r plus mu v naught t upon the coefficient of this, which is mu v naught, okay, and the limits going from t equal to 0 to t equal to t. So r by mu, take this outside, and upper limit, so ln r plus mu v naught t minus lower limit, okay. So lower limit is this. So the distance traveled is r by mu natural log of r plus mu v naught t divided by r, because you can use the property that log a minus log b is log a by b. So s as a function of time is this. And angular displacement will be s divided by r. So that will be 1 by mu ln 1 plus mu v naught t divided by r. So this is your angular displacement, and this is the distance traveled, not the displacement, which is basically the arc length as a function of time. Okay. Okay, so hope this is clear. So Aman, both the parts are clear.
Yes, sir.
Okay, now next we will discuss one of the questions from HC Verma. Then Aman, I'll come back to exercise 5. So alternately, I will solve from HC Verma as well as from module. Okay. So this is a common doubt that a couple of people have asked. Question number 63 of HC Verma. Okay. So work by energy. Question number 63 of HC Verma. Just go through it first. I'll explain that next. So HC Verma, work by energy. Question 63. While you're noting this down, the others can just go through this question number 63. We will start this. Okay, let's work out this question from HCV, then we'll come back to the module again. Kevin, work part module, which exercise? Question 53 and 51. Exercise 5. Okay, we'll come back to that. Yeah, so currently let's work out this 63rd question from HCV. So this question can be done in two ways. One, directly by using the formula of center of mass, even though at the time when you had done work by energy, you had not done center of mass formula. But if you use that formula, we can avoid the integration over here. So anyhow, let me discuss. So what is happening is we are having a spherical surface like this. Smooth spherical surface. Now there is this chain which is lying over here, let's say, from the point A to B. So this is a chain of mass m and length L. L is less than R. Okay. So with respect to this origin, first we have to find the gravitational potential energy. So what we do here is we use the formula for position of center of mass. Okay. So if this is a chain, the center of mass of the chain will lie where? It will lie on the perpendicular, on the angular bisector at some position like this. So let us say this distance is OC. So this distance OC will be equal to how much? It will be, if this total angle is theta, then this is the angular bisector. Okay, so theta by 2. So OC will be equal to R sine theta by 2 upon theta by 2. This is center of mass formula for circular arc. If you remember this formula, you can apply it directly. Okay. So that will be now, that will be R sine. Now theta is what? The total angle subtended. So this will become L by R, but half of that. So L by 2R divided by L by 2R. So 2R square by L. Okay, so that is the distance OC. So if this is our y-axis, then the y coordinate of the center of mass will be this point here will be the y coordinate of the center of mass. Okay. So in this triangle you can see this is the y coordinate of the center of mass and this angle is theta by 2. So this y coordinate will be that distance OC cos theta by 2. So that is 2r sine theta by 2 divided by theta cos theta by 2. So it is, you can also write it like this, it is r sine theta divided by theta. that is R sine L by R divided by L by R. So R square by L sine L by R. This is the y coordinate of the center of mass. So we can write the potential energy with respect to O as mgy. Okay, so this is the center of mass shortcut way of calculating the potential energy. Okay, I'll also show you the integration method next. Okay, so Shravani and Shikhar, hope this question is clear to both of you. This part is clear to both of you. Now, suppose you don't remember the formula of the position of center of mass, then you can always quickly derive it this process by integration. So alternatively, what we can do is you can use integration. So for that, what you will do is, now let's say this is our chain again. So at some position theta, or theta is a variable, okay, you will take a small differential arc, r d theta. So this will become like a particle, become a particle of mass dm, which will be m by L into that small arc length. So m by L r d theta.
Sir, will not take linear mass density into consideration.
Yeah, linear mass density. Na m by L is linear mass density.
Linear mass, yes.
So dm is lambda ds. वही क्या? Okay. Now ये वाला जो particle है, इसका y coordinate कितना है from here, from this origin? Its y coordinate is r cos theta. Okay. So this particle's potential energy with reference to O is dmgy. So that is m by L r d theta into g into y, which is r cos theta. So that is the energy of that particle. Okay. So the potential energy overall is the summation for all the particles from A to B. So that is now just keep everything together. So mg by L r square cos theta d theta. This has to be integrated from the point A where theta is 0 to the point B where theta is L by r. Okay. So if you do that integration, you end up getting mg r square by L sine theta integrated from theta equal to 0 to theta equal to L by r. Using the limits, you get this. So it's not really a lengthy integration. It's just one extra step. So this is the second method for this potential energy part. Now let's come to the B part. So release the chain from this given position, and you have to find the kinetic energy when it is slit through an angle theta. So now next part. You release the chain from this position, say AB. Now it started sliding. So this is, it started from rest over here. Now after some time, the chain has reached here, let's say, to the position CD. Okay. So your initial potential energy was when it was at AB. So we just saw that it was mg r square by L sine L by R. Okay. Now your final potential energy is when it has come to the position CD. So whether you go by that center of mass method or by this one, you will see that this will become mg r square by L, but this will change. If you are doing the integration, your limits would have gone this cos theta d theta. Your limits would have gone from the point C, where the value of theta is now this angular displacement is, let us say, theta naught. Okay, so this angle is also equal to theta naught. So here at C the value of theta is equal to theta naught, and at D the value of theta is theta naught plus L by R. So limits are going like this. They're going from theta equal to theta naught to theta equal to theta naught plus L by R. So it will become mg r square by L sine of the upper limit, so that is theta naught plus L by R, minus sine of the lower limit, that is sine theta. So this is your potential energy. So this term will be the angular displacement plus L by R minus angular displacement. So this is where theta naught is the angular displacement from t equal to 0 when it is at EB to t equal to t when it is at position CB. So this is this one. So by this time it has now got some linear speed v. So now change in kinetic energy plus change in potential energy should be equal to 0. So half mv square should be equal to u initial minus u final. Yeah, see Shikhar, when your chain is at the position CD, for the potential energy, you were integrating this quantity, no? You were integrating this quantity. Okay, this quantity was being integrated. Okay, but now we're integrating it from C to D. So at C, what is the value of theta naught of theta? It is this. And at D, what is the value of theta? It is theta naught plus L by R. And at C, the value of theta is theta naught. So limits become theta naught to theta naught plus L by R. Is it clear now, Shikhar? Okay, so you do that and you apply work by energy. So you get this. Okay. So you see this term, when you're subtracting these two, you end up getting something like this. Sine L by R minus sine theta naught plus L by R plus sine theta. Okay. Where theta naught is angular displacement. So now next part, the last part, we want to find out the tangential acceleration, that is dv by dt. When the change starts sliding, you want to find this value. So what you can do is you can take this equation, half mv square is equal to mg r square by L sine L by R minus sine theta plus L by R plus sine. Okay. And you can differentiate both sides of this equation with respect to time. Okay. So differentiation of this term will become mv dv by dt, and differentiation on that side, this is a constant. Okay. Now differentiation of sine of L by R will be 0, but differentiation of this term will become cos theta plus L by R into d theta by dt. Okay. And this term's differentiation will become cos theta naught into d theta by dt again. You get this kind of term. Okay. Now in this, remember d theta by dt is the angular speed, okay, which is v by r. So mv dv by dt is mg r square by L. Now we can take d theta by dt common, and that will become v by r. So you can cancel the common terms. So dv by dt becomes gr square by lr. So that will just become g into r by L into cos theta naught minus cos theta naught plus L by R. Okay. So this is a general expression. So dv by dt at t equal to 0, that will just become gr by L into 1 minus cos L by R, because at t equal to 0, theta naught was 0. The angular displacement was 0. So that is the third part of the question, or the C part actually. Okay, so again, Shavani and Shikhar, hope this is clear. Okay, very good. So finish writing this down. Next, we'll discuss something from the module again. Okay, after we finish work per energy doubts, Nikita will discuss heat and thermodynamics doubts. Anyway, that is a current ongoing topic, so we'll discuss doubts of that in class also. Whereas doubt session is an opportunity for you to pick up any questions from the previous topic or topics. You can ask doubts from, when we finish work energy, we can pick up doubts from other chapters also. Okay, let's look at this question next. So this is from exercise 5 module. Okay, so this is a elastic cord. Just think of it like a spring. So it has some spring constant and it has a natural length. And right now it is at natural length, and that is given to us as 40 centimeters. Okay. There is a coefficient of friction equal to 0.2 here. Okay. The plank is of 1 kg mass. Okay, so the slipping starts at a particular time. Sorry, the bar is of 1 kg mass, not the plank. Okay. So slipping starts when the vertical cord deviates by 30 degrees. Okay, so let's understand the diagram when that has happened. So when this is deviated by 30 degrees, it just about starts to slip. So when this angle is theta, this has become some L plus X. So as you can see, is equal to cos theta. Now there will be a tension of px type acting. So the plank is being slowly shifted to the right until the bar starts sliding. And this occurs at the moment when the cord deviates from the vertical by 30. So we have to find the work that has been done. So this is being moved very slowly. So this F is a variable force such that it is moving this very slowly. So its velocity is 0, acceleration is 0. So up till such time, let us say okay, what is happening here is static friction is acting on this block. So if you look at the block's free body diagram, there is
So
spring
why
force
did we take
Kx.
the tension like a spring?
Because it's given to us as it's an elastic and light cord. Understood na beta?
Yes, sir.
And initially it is non-deformed. Okay, so that's why. Okay,
Okay,
so
sir.
that's why. No? Okay, so ये ऐसा it's acting at an angle theta, right? Normal reaction is acting vertically upwards. Mg is acting vertically downwards. And okay, so now when it's ready to slip, that time this static friction will just become equal to the limiting value, right? So at theta equal to 30 degrees, static friction just about becomes equal to mu n. So it just starts to slip. Okay. So from that we will get. So first of all, geometrically, this equation is giving us L, which was 40 centimeters. So 40 centimeters upon 40 plus x is cos 30 degrees, which is root 3 by 2. Okay. So from this x's value we will get, and that will be how much? It will be 2 minus root 3 by root 3, right? Or we can just write it directly as just cross multiply. So 2 by root 3 times 40 is equal to 40 plus x. So 2 by root 3 minus 1 times 40 centimeters. This is the value of x. Okay. And from this diagram we can see, applying this condition, you will get that kx sine 30 degrees is equal to mu n, and n is equal to mg minus kx cos 30. Okay. This is the other equation we get. Now basically what we have to do from here is we have to find the work done by F, which is basically the change in potential energy of the elastic string, which is half kx square. Okay. So it's just this. Okay. So from this equation, actually, we can just find the value of kx. Okay. And this equation is giving us the value of x. Okay. See, kx here will become how much? It will become mu mg 2 times mu mg upon 1 plus k root 3. Sorry, 1 plus mu root 3. Okay. So substitute this thing here. Okay. And substitute the value of x directly over here. So you got the work done. Kevin, is this clear? Okay. So the interesting thing in this question is we don't need to separately calculate the value of k. We can directly substitute kx by 2 and we can directly substitute the value of x. Okay. Okay, next up, do another question from the module. Exercise 5 again. Yes, Nikita will discuss 64 after this. Okay, so in this question, you have to apply the constraint relation to find the relationship between, the speed of the outer two blocks and the middle block.
Sir,
Yeah,
sir, we'll use the velocity trick, right?
you mean the virtual power trick?
Yeah.
Yeah, you can use that. That will be the easiest way.
Yes, actually. Yeah.
Otherwise, you can use calculus and thread length conservation. But
Yes, sir. That also we can use.
Okay, so just set up the constraint relation. I'll put it up on the board. Okay, so the system was initially like this, with C starting from the point O. So you had kept this thread, suppose, stretched out like this. From here we release it. Okay. So this distance is 2a, and all the three masses are identical. Okay. And it starts from rest here. Now from here, it is going to this position next. It's going to this position where these two blocks by symmetry will be at the same height. And this one is here. Okay. So now if these angles are theta, so let's say these two are going up with some speed v1 each, and this one is coming down with a speed v2. So if I use virtual power method, power developed by tension should be 0. So plus tv1 minus tv2 cos theta should be equal to 0. So v1 is equal to v2 cos theta. So one is you can use that, or you can also use the concept of approach and separation velocity. If this is block A and this is block C, and if this point where this pulley is attached is P, okay, then approach velocity of the point A towards the point P should be equal to the separation velocity of the point C with respect to the point P. Okay, because thread length is constant. So this is an alternate approach that you can take. Okay, so you can see the block A is directly moving towards the pulley P, so the approach velocity is v1, but this point C is actually moving. See where this block is there, that point, it is actually moving vertically downwards. So C is moving like this at v2, whereas the point that we are considering where the pulley is there, that is this point P. So with respect to this line, C's velocity is such that this angle is theta. So C's velocity is component along this line. That is how much? It is v2 cos theta. So that is the rate at which C is at this instant. It is separating with respect to the point P. Okay, so that concept I've just explained again over here. So this is another way in which you can solve the constraint relation. Okay, so this is clear, I hope. Constraint relation, first of all. Same thing. Okay, the next thing is work by energy. So for work by energy, we have to understand that, okay, if this block C has come down through a displacement, I'll just draw another diagram. So this one has come down through a displacement of S, let's say. So these two have comparatively gone up by some displacement S prime. Now can you tell me how much S prime will be? So thread length conservation. No? So S prime will be this hypotenuse, let's say Z minus this. A, right? So S prime will, yes, okay. And once again, in terms of theta also we can define them. So if S is equal to, you can see A by S is tan theta. So S is equal to A cot theta. Okay. Then S prime will become E by Z is equal to sine theta. So it will become A cosec theta minus cot theta. Okay. Now from our work by energy, change in kinetic energy plus change in gravitational potential energy should be zero. So 2 times half mv1 square plus half mv2 square. This is the change in kinetic energy. Okay. Minus mgs plus 2 times mgs prime is equal to 0. So v1 square plus v2 square by 2 is equal to g into 2s prime minus s. So this is our second equation. And this is again a constraint relation. We'll take this as our equation 3. Okay, so now we have to just substitute all this. Now it is given to us that the distance OC, that is Z in my equation, is 4a by 3. So if Z is equal to 4a by 3, that means sine theta is 3 by 4. So, or we can just substitute directly over here that in this equation, Z is equal to 4a by 3 means S prime is equal to a by 3. Okay, and S we can just get like this. Square root of Z square minus a square. So square root of 16 by 9 minus 1. So a root 7 by 3. That is the value of S. Substitute these over here. So v1 square plus v2 square by 2 will become g into 2s prime. So that is 2a by 3 minus s, which is a root 7 by 3. So v1 square v2 square by 2 is equal to ga by 3 into 2 minus root 7. This equation, and we have this constraint relation. v1 is equal to v2 cos theta, and cos theta you can substitute. Yeah, so yeah, Shikhar, I'll explain the virtual power method also, but in this equation, how much will substitute cos theta? Okay. So this side is A, this side is 4A by 3, and this angle is theta. So you can see that this side is root 7 by 3A, na? That is what we just got.
So the base is
Cos,
4a by 3.
sorry?
So the base is 4a by 3. OC is 4a by 3.
OC, na?
So you're taking BC as
Oh,
4a
achha,
by
achha,
3.
OC, O is that point. Okay, okay. Yeah, yeah, sorry. So wait, so I'll just change these values. So it is S which is actually 4A by 3. You know? It's not Z. Yeah, correct. This point is O. So this point is O and this point is C, correct. So then this becomes much simpler actually because it becomes a known triangle. So S is equal to 4A by 3. Okay, so this is a, you know, this is tan inverse 3 by 4. So theta becomes 37 degrees. Okay, and Z will become 5A by 3. So from this you can see that S prime will become 2A by 3. Yeah, but anyway, is this clear now, Kevin? I mean, this is all right now. Okay, so let's just complete the substitution. So this becomes V1 square plus V2 square by 2 will become G into 2S prime, which will become 4A by 3 minus S, which was, oh, it's coming out to be 0, is it? Is that the answer?
So you
Yes,
have
sir.
to show that.
We have to show that. Okay, so the blocks come to rest at that instant. Okay, but if we had taken some different value of theta other than 37, so for example, if we had taken 53 or something, then we would have got a non-zero value here. Okay, so anyway, now this constraint relation becomes irrelevant because this is coming out to be 0. So that means at this instant V1 is equal to V2 is equal to 0. So this is actually the maximum displacement that the system will have. So this will be an oscillating system. It will keep going up, down. Right? This is clear? Yeah. So show that C has fallen a distance this before from O. No, just a minute. Why are we getting the velocity as 0 then?
Sir, in the question, it is written system is at rest.
No, no, sorry. वो उल्टा है ना 3a by 4 जब है तब उसका velocity इतना है. 4a by 3 पे rest पे आ है. So that we have got. Okay. Whereas it's like a second part. Now also show that when C has fallen 3a by 4, at that time this velocity of which one is this? C is this much. Okay. So that's like a second part of this question where you now replace S with 3a by 4 instead of 4a by 3. So when S is 3a by 4, okay, that time your theta will come out to be 53 degrees because this triangle is like this at that time. Okay. So that time this is how much? This is 5a by 4. This Z. Okay. So S prime will become Z minus A. So that will be A by 4. Okay. So at that point of time, our equations will become like this. V1 is equal to V2 cos 53 So V1 is equal to 3 by 5 V2. Okay. And this equation V1 square plus V2 square by 2 is equal to G into 2s prime. So that will be A by 2 minus 3A by 4. This is giving us a negative, no, wait, it should not make sense. Oh, I've written this in reverse. This should be S minus 2s prime. That's why I've taken this term to the other side. So it's S minus 2s prime. Okay. So this is fine. But here it will be a other way around. S minus 2s prime. Okay. Now which one we have to find? We have to find the speed of C. And the speed of C we have taken as V2. Right. So substitute V1 as this over here. So 3 by 5 V2 whole square plus V2 square by 2 should be equal to G into S is now 3A by 4 minus 2S prime, which is A by 2. Okay. So this should be all right now. So 9 by 25 plus 1 by 2 into V2 square should be equal to 3 by 4 minus A by 2 will give us how much? A by 4. So GA by 4. So just check out, is this giving the value? So this will be how much? 25 plus 18.
Forty-three.
43.
Is this the value they've asked?
Yes.
Okay, so this is a method. Yeah, so Shikhar, I'll just explain to you the constraint relation again. My virtual power method. So the power delivered by tension within the system should be 0 because tension is an internal force. So tension is acting like this over here. Okay. Now this block is coming down with a velocity v2, whereas both these blocks are going up with a velocity v1. Okay. So now the virtual power concept is that the net power delivered by tension should be 0 for the system. Okay, this statement is clear now, Shikhar? Okay. So power delivered by tension on A plus power delivered on B plus power on C should be 0. Okay. Now power delivered by any force is given by the relation F dot V. Okay. So over here you can see if this angle is theta, this half angle is theta, then what is the angle between the velocity vector V2 and this tensional force T? This angle is 180 minus theta now, because this angle is theta. So how much power each of these tensions is delivering at B? It is 2t cos of 180 minus theta. So that will become minus 2t into V2 cos theta. Whereas at A is delivering plus t V1, because the angle is 0 between velocity and this tension. And at C also is delivering plus t V1. So that's how we get 2V1 minus 2V2 cos theta is 0, or V1 is equal to V2 cos theta. So hope it is clear, Shikhar.
Yes, ma'am. Yes, sir. Understood.
Okay, good. Okay, so next we'll go back to a question from H.C. Verma, the last question of work by energy, question number 64. Yeah. So this is a bit of an odd question, because we actually, what we have to do in this question is we have to solve work energy theorem in a non-inertial frame, which is generally something that we avoid doing. We try to apply work energy theorem in inertial frame always. Okay, but I'll explain how it can be done over here. So what's happening is there is this smooth spherical body. Okay, and it is being made to translate with a constant acceleration E. Okay, and we, I don't know, it's not given, but I think we have to assume that it's translating horizontally. The question just says a smooth sphere of radius r is made to translate in a straight line with a constant acceleration A. Okay, but I think we'll have to assume that that acceleration's direction is horizontal. So this sphere itself is accelerating horizontally with an acceleration A like this. And the surface of the sphere is smooth. And with respect to the sphere, a particle is released from rest over here. Okay, so this is the situation at t equal to 0, and we are in the frame of this sphere. So we are in this non-inertial frame. So we can see that on this particle, the forces which start acting are pseudo force, weight, and normal reaction. That immediately gives a tangential acceleration in this direction, and the particle starts sliding like this. So it's in a non-uniform circular path. So at some time t, when the particle reaches here, forces acting at that point of time are like this. But more importantly, by now the particle has a speed v in this frame. So in the non-inertial frame, we can say that work done by pseudo force is equal to change in kinetic energy plus change in gravitational potential energy, or we can say that work done by pseudo force plus work done by gravity is equal to change in kinetic energy. This also we can say, this also we can say, but this is with respect to non-inertial frame. Okay, the change in kinetic energy is in the non-inertial frame. Okay, so this u and this v are in the non-inertial frame. So now this pseudo force is a constant force. Okay, so this plus this, this. Now in this also S is the displacement in the non-inertial frame. Okay. So if you take X and Y axis like this, you can see that the displacement is, this angle is theta. It is minus r sine theta I cap minus r into 1 minus cos theta j cap, and the pseudo force is minus ma I cap, and mg is minus mg j cap. So this equation is reduced to this. This kind of. Okay, so V will become square root of R into this plus this. Sorry, the 2 comes outside. So 2 comes from this half mv square term. So anyhow, just go through this once and let me know if there's any doubt. I think some 2 or 3 people have asked this question. Okay, next question. Again from module exercise 5. So just go through the question first, then we'll discuss. So basically the two spherical objects are starting from rest, okay, and they come sliding down symmetrically on either side. So use work power energy to find the tangential speed as a function of theta, and then make the free body diagram of the spherical bodies to find the contact force between them and the circular pipe, and then make the pipe free body diagram to find the contact force between the pipe and the ground. Okay, Snikita, I'll take you back to the previous question solution.
Done, sir.
No? Okay. All right. Let's come to this this module question now. Okay. Yeah. So in this question, what is interesting is that when the two spheres initially start their motion, they are in contact with the inner surface of the pipe. They are in contact with the inner surface of the pipe, whereas by the time they pick up some minimum amount of speed because of the centrifugal force acting on them, they'll become in contact with the outer surface of the pipe. So when they're in contact with the outer surface of the pipe, okay, the normal reaction that they are applying on the pipe is radially outwards instead of being radially inwards. So that is why the pipe comes in danger of losing contact with the ground. Okay, so what is happening here? So it's just telling you that okay, so when the two spheres start out from the top, their speeds are zero. So the normal contact force acting on them is like this. It's almost about mg. But by the time they come to some kind of position here, let's say, now what is happening is it's possible that the normal force acting on them is the normal force is inverse. Okay. So the normal reaction acting on the pipe is outwards. Because by now they got speed B. Okay. Okay. So in this diagram, what is happening is n plus mg cos theta is equal to mv square by basically mv square by r is become greater than mg cos theta. Okay. So the spheres are in contact with the outer surface. This one is the outer surface, and this one is the inner surface. So here they are in contact with the inner surface. But by now they've come in contact with the outer surface. So this is clear now, I hope. Okay. Now from here to here, use work power energy. I mean work energy theorem, you can say. So this becomes our second equation. Okay. So substitute this over here. And we get n as a function of theta. Okay. Get this. Now you make the FBD of the ring or the circular tube kind of thing. Now that is experiencing these two normal reactions here. Okay. Its own weight, let's say m prime g like this, and normal reaction with the ground, say n prime. So normal reaction with the ground is its own weight minus 2n cos theta. Now substitute this here, so we'll get like this. Okay. So now you can see, take this function two cos theta into 2 minus 3 cos theta. Okay. So n prime is like m prime minus small m into this function times g. So n prime's minima is this function's minima. Sorry, this function's maxima because you're subtracting it. Into g. Okay. Now this function, if you think about it, think of cos theta like a z. Okay. And obviously z is between, in this case, 0 and 1 only, because we'll take theta to be acute. Okay. So this function of theta can also be written as 2z into 2 minus 3z. Okay. So this function's graph is like this. This function's maxima is at 1 by 3, z equal to 1 by 3. So it is 2 by 3 into minus 3 into 1 by 3 is 2 by 3. So the maximum of this function is 2 by 3. Okay. So this normal reaction's minima is m prime minus 2 by 3 m into g. And this minima occurs at theta equal to cos inverse 1 by 3. Is the question clear, Kevin? I've avoided using differential calculus for maxima minima. I've just used substitution. So from this step only I could have used calculus, that differentiate n prime with respect to theta, put it equal to 0 and all that. But that was not necessary because I could see it's a quadratic function in cos theta. So just think of cos theta like a new variable, but only that variable has a limited domain. It's not going up to infinity or something. So within that limited domain, we had to find the local maxima of that function so that n prime has the global minima. And then the condition that n prime should never become 0 is that m prime should be greater than 2 by 3m. So then in that case, normal reaction n prime with the ground cannot become 0, and otherwise vice versa, it can become 0. Okay, people, so hope this question is clear. And with this, more or less, I want to wind up the work by energy doubts. Okay, so next session, when we pick up doubts again, we will look at another chapter for doubts. But in the meantime, if you have more doubts in work by energy, please send me on WhatsApp and I will send you some hints, etc. Or during the mentorship sessions, we can discuss. Okay. So that's it for today's session, people. Wish you all the best.
Thank you, sir. Bye.
Thank you, sir.
Okay.
Bye.
Okay.